so let's do I/O and wiring. Here's kind of what I've come up with that allows me to wire things up and not make mistakes anymore. And part of this is very mechatronics related because you're dealing with devices that have the different parts that you want to hook up are in different devices. And the trouble with schematics, you know, each of these devices has schematics. Those are interesting. We actually need some of the schematic parts of them, but we don't need the whole schematic. We're only interacting with a small part of the component. So for instance, let's say we had an Arduino. Let's say we had an L298. You'll notice the first thing I'm doing is I'm drawing boxes, big boxes. And over here, we're going to have a power supply. Or supplies. So we need schematic elements because we're going to make I'm going to skip ahead. I'm going to come back to this in a minute. But if I ask each of you to, I want you to draw a flashlight, an LED flashlight. And I've changed it. It used to be just a flashlight, but LED flashlight is so much more like what we're doing than anything else. What are the key things you need to build a flashlight? The 3 circuit elements you need?
A battery, resistor.
You need power, right? You need a battery in that case. You could build one without a battery, right? Right. So you need power.
A switch.
Switch.
And an LED with a resistor.
And a load, right? The resistor is key. The LED is what you want to do. That's the key. But if you just hook up an LED, it goes poof. So you add in a load and the main reason you add resistor in there is to do what?
Limit current.
Yeah.
So it doesn't destroy the LED.
Exactly. You got to limit every circuit you do. You got to have something in there to control the current, to limit the current. And so you'll hear me say, I'll know when you're done with your design because you'll know the answer to that. Okay. So flashlight, pretty simple, right? We could run a switch and then LED. Right, pretty easy. And the easy thing about and in fact, then you can calculate I is super easy, V, R, L, and this has a time. If you decide to count the voltage drop across the diode, that's fine. You don't have to. And if you wanted to be truly accurate, you would. But remember, we're not doing much that's super accurate. We're trying to pick the size of the wire, and we're trying to make sure it doesn't burn up the transistor. Because what element or what are we really trying to do? When you look for what I equals, you're actually trying to accomplish a couple things. One is you want to limit it. So because this has a current limit. This has a current limit. And that has a current limit. Right? So when you buy a power supply, you buy one at a certain voltage, but the next thing you look at it is you look at that little tiny wiring on there and you look for what?
The current rating of the power supply?
Okay, and what does that mean? Current, yeah, you're looking for the current. What about the current are you looking at? It has a number, right? What's that number tell you about how much current? Does it tell you how much it will supply or how much it can
supply?
Can supply. Okay. How much current is going to come out of that power supply? That's what depends on your resistance, right? So I always want you to think about current is drawn out of it according to what the load is. And for some reason, a lot of people get this far along thinking, oh, it says 2.6 amps. That means 2.6 amps is going to come out of it. No, that means it can supply up to 2.6 amps, meaning if you have 3 circuits or a circuit that takes a third of an amp, you can run 1, 2, 3, 4, 5, 6, 7, 8 circuits for 2.6 amps, right? And you'll be okay. You run 9 circuits, what happens? You're going to have an overloaded power supply, and it's either going to brown out, die, kick a breaker, blow a fuse. And if you notice, I gave you some fuses, those little brown fuses. It's because you didn't do enough I equals on it, or you hooked it up backwards, one of the two. So each of these devices now are in our circuit that we're aiming at, the actual control circuit. This switch right here, that switch is most often it's not a switch. It is a transistor. So voltage supply, yeah, you're going to do that. The switch in the LED is going to be a transistor instead of a physical switch. Okay. And then you've got some sort of resistance to limit the current. And you have the whole purpose of all of this is to turn on the light, an LED, right? That's so that you get light out of it. So you run a bunch of current and you size all the devices, I equals. Really easy circuit, isn't it? You can do this in your, and the cool thing is you can even do this. You can say, hey, let's run 2, right? Can you run 2 things off of a power supply? You can. That's where you took those classes for parallel and series and Kirchhoff, and you don't have to remember much about Kirchhoff. But you do know that those are 2 circuits, and there's only one power supply, and that's the 0.3. So it's really simple circuit stuff. The problem is we go back to here. The devices are all in different places. Okay, so let's do this. Power supply. Where's the power supply? Well, let's just draw it in right here. Power supply. Probably, I'm going to actually, most of the time, you're going to have dual power supplies, but we'll call this one the big one. This is V bus. I don't know why they call it a bus voltage, but it's probably because that attached at some point it attached the big thick bars, and they call them bus bars, and it's so it's bus voltage. It means that's the high voltage of the system, and that's what you want to run inductors. Inductive loads mean high voltage. Okay, so that's pretty simple. We know that's there. So let's draw. This means connection points. I'm giving you this Mechatronics diagram. It's never seen anybody else do it except me and all the engineers I taught to do it. But this is how you figure out how to wire things and never make mistakes. And what I'm doing is I'm putting the boxes on the page. I'm taking the whole page, putting the bot. Yeah, Mary, you're laughing at me because you've had all this stuff. You guys that had 140, you got all this before, right? So you put the boxes on the page. Then you put the circuit elements in the box. So what's the circuit element in the amplifier or the drive, the L298N? What is the circuit element that you're driving in that?
Transistors.
Well, hold on, because all of a sudden now we have two different things going on. There's two parts. When you have a transistor, there's two circuits, isn't there, to a transistor? There's this circuit that turns it on, and there's this circuit, right? Remember this? So this is milliamps. In the inductor, in the H bridge, the key to this transistor, this power transistor, this is amps. So it allows you, this is really, really key. It allows you to turn on and off amps with milliamps. So there's two circuits you got to run to make this thing work. One is probably 5 volts to turn on and off the transistor. Well, you're not going to do that with that. So you're going to need a power supply for that circuit. You're going to need a different power supply for that circuit, for the amps, right? So it's getting a little complicated. We got two circuits in the L. So let's deal with one. Let's first deal with the 298N part of things. Let's deal with the power part of it. What's in the power part of it? Well, you are essentially, if you notice, whenever I drew that, I always drew the transistor and I always left off the base. I never even drew the base of the transistor. I drew the collector emitter part and oops. And it was, there's the motor winding, and then it was to the collector emitter junction, and then it was to ground, right? And so let's go ahead and wire this up. This is what we're after. And previously when I drew that, I'll just draw this out. This one's a pretty easy one. There's only one thing you gotta, this winding here is the resist, that has a resistance to it. So when you go run through the winding, there's your resistance. And the only other thing you gotta do is make sure you go through the transistor the right way. So we need current to flow. When that's on, current has to flow that way. All right, that's easy. Let's draw it. Get out your pencil. This is where the pencil comes before you don't get out the screwdriver and do this, right? This is so simple that you just say, oh, well, wait a minute. Okay, how about this? Let's run that. And there. Okay, now this, unlike the LED, this is an inductive load that you just wired up. And then you take out your finger and you make sure you got a complete circuit. So you start at the positive of the power supply and you say, oh, what is this yellow line? This yellow line that's a wire you got to hook up. Okay, even better, to order to make this drawing complete, you add one more thing, you label stuff. All right, so let's label it. We'll label this plus. We'll label that minus. We'll label this will say V bus or something. And this will probably say GND on it. Okay, now you're done. That's it. And now you know a bunch of stuff. You know schematically, electrically schematically, you know that you've got power through, it's going the right way through there. You're looking for those three things. I got power, there's the switch, there's the load, there's another switch, and Boom, we made it back. And you always got to get back to the ground of that power. We don't want to get back to that one. You got to get back to that one. That's why I draw power supplies now, as opposed to like electrical circuits where they just, I drew that before, they just draw the ground in the air. To me, there's no such thing anymore as a ground in the air. It's what power supply is it? Where's the plus? Where's the minus? Complete the circuit. Then I can just take my finger around. Easy. Okay. So that's the power side of that. What's the I/O side, the communication side? That was easy because both of those elements are in one. Okay, so now when we do the Arduino, where's the load? Well, let's add this in. Okay. And somehow we got to get out of this. I'm not sure what we're going to do there. Oh, well, they got it figured out, I presume, somehow. Probably they have some sort of other gate to do that. That's going to be interesting, isn't it? Coming back to that ground. I'll have to look at the circuit of that, see what they did. But the one thing we know is that here is something that ultimately we want current to flow through that. But we're missing some things. So where are we missing? Well, where's the switch?
From the microcontroller.
Yeah, it's over in here, isn't it? It's in, so we'll just call it this output is right there. Now what people tend to do is they tend to have a wire and they say, oh, output to input, and they just draw a line. And to me, a line isn't what we're after. We're after circuits, not hookups. We're after circuits. And so what we need to know is what's behind this. And they could do it different ways. They could have pull-up resistors. So in other words, you need to get to find out what's the circuit that's inside the Arduino. Probably there's some pin here that says 5 volts. Okay, what's the first thing that should occur to you when it says 5 volts?
You need 5 volts to run that microcontroller?
Oh, is that your assumption? Maybe. What's the other assumption that somebody could easily make?
The outputs are going to output 5 volts.
Yeah, that's the question. That's 5 volts. Is it in or out?
Specifically on Arduinos, usually it has the 5 volt pin that you'd use for like digital ins and stuff.
Okay, what was that first word you used there, Connor? That's a key word.
Typically, I think.
That's a
Is
good
that what I said?
one.
Or specifically, I think I
it
said.
was presumably, right?
Oh. Yeah.
So this is where I need you to listen to that little, I always call it the little bird that sits on my ear and talks to me and tells me, you're guessing, you're guessing. You can't guess. When you hear yourself say something like presumably, whoa, that's a big signal. You got to go find out. Is that 5 volts in or is it out?
That's what voltmeters are for.
No, that's what data sheets are for. You can't really tell. It could be internally pulled up. It could be, you can tell, but if power is off and you measure it in a state where it has internal switch control. Voltmeter is helpful when you want to know if there's something wrong or what's going on. But in general, the way you find out is like, keep reading. Is it 5 volts in or 5 volts out? And if it's 5 volts out, oh, it's a supply. We might be able to use it down here. They might have put a 5 volt supply for you to use. And if they did, what's the next thing you want to know about that 5 volt supply?
What its maximum current output is.
Exactly. Imax. First thing you want to know. Oh, it's an output. How much can I use? Oh, it's only 200 milliamps. Oh, okay. Good. Oh, how can you use it? The other thing you kind of want to know is it designed for inductive loads or resistive loads? Huge difference. From now on in the rest of your career, when you see a load, you need to think, is that an inductive load or a resistive load? And the difference is in resistive loads play V equals IR exactly. And there is no such thing as inrush current. An inductor has an inrush current that uses, when you apply voltage, it's not just this constant V equals IR, it's a changing current, and it draws a lot more at the beginning. Every time you run an inductor in a motor, it's an inrush current. If you hook up your air compressor and run it off the circuit, I did this one time. I was trying to run a 0.5 horsepower air compressor off of a 3 horsepower generator. It's no problem, you would think, right? 3 horsepower generator, 0.5 horsepower motor, except it's an inductive load. You plug it up, you plug it in, and you turn it on, and it goes, "Bruh," because that inductive load draws a ton of current right at first that the generator can't supply. The good thing is, though, about wall voltage is the supply behind the wall voltage is the grid. And it has huge inrush capability to the extent that you fused it properly and whatnot. And so you've got to think about loads from now on. Is it an inductive load or not? A radio has 2 parts to it. It's a resistive load. When you hook up a radio, it's a resistive load for the circuitry. But as soon as you key up the radio, it's an inductive load for the antenna. A pump, a electric pump, you know, like a well pump, for instance, has an AC motor on it, inductive load, inrush current. The kind of circuit that we just drew here, inductive load, inrush current. This voltage here, this power supply needs to be a different kind than the 5-volt wall ward. If you wanted to run this off at 12 volts and you found a 12-volt supply that was a little switching supply that was designed for resistive loads, it would absolutely not work to drive that inductive load very well. I mean, it'd probably just blow it up. I did this one time. I was trying to find something to work on a radio, and I just grabbed a bunch of different 12-volt supplies, and they were all 2 to 3 times the amount of current. And every time I keyed up the radio, it shut off. Finally, I hooked one that was like 5 times the amount of current. I keyed up, no problem. And it's because it's like, oh, duh, Nick, it's an inductive load. So from now on, when you hook up loads, inductive, especially mechatronic, you mechatronic engineers, inductive load versus resistive load. Okay, so here we had inductive load, but this isn't inductive. We're now dealing over here at the control side of things. We're dealing with resistive loads. Okay, so we got to see if that's 5 volts in or 5 volts out. Typically, somewhere in this output, they're going to have somewhere in here is going to be, you know, there's some switch of some sort in there. Probably it's a transistor, which means probably you better run current the right way through it. But I would go ahead and draw that circuit element in there because you need, now this is where the switch is. So if we did this, I'm just going to draw this. This is wrong, but I'm going to draw it anyway and then revise it. But if I did this and this and this and this and then, well, you see the problem I got into, right? I don't want to go through there. So can I just go back to there? You know, do I have a pin? Well, that's a problem. You know why that's a problem? This is where I pause because I drew this thing and immediately I'm going, I see a problem because I'm taking my finger around. How's this going to work? Watch me take my finger around the circuit I just made if I made that circuit. Like, okay, so let's go here through this wire. Wait a minute. This is all wrong. This is all wrong. And that's, so hooking this to this may not have been it. I'm not sure what it is. You'll have to go look it up. But that's the beauty of doing this is you're looking, it's like, wait a minute. That can't work. Because I took my finger around it and it wasn't an LED flashlight circuit. It can't work. That's all wrong. Get rid of that. Boom, boom, right? Get rid of all that stuff. I'm backing up there. Let's try again. Maybe I needed to go maybe I need to go in a different way. Maybe this is a 5 volts out instead of a 5 volts in, which is a problem. So that's where you start needing to label things, look things up, and label the pins and draw wires between them, and then find your flashlight. Every single one of these is going to be power, switch, and load. So every time you draw a circuit, power, switch, and load. And then when you've got it, it's like, okay, nothing's blown up. Then you have one last thing to do, and that is how much current's going to flow in that. And you need to know this for a couple reasons. You need to calculate I equals, and that's easy. V, R, a couple of voltage drops along the way. There you go. That's right. Pretty easy. Now it's going to get a little more complicated when you start to pulse width modulate things, because you need to put in a box in here. You need to have some sort of PWM capability, because we want to drive it a little bit different. I'll let you work on that. But two reasons you want to do I. One is to blow things up, power supplies or components. But the other is, see this piece, this yellow wire right here? What size wire is that? Is it small? Is it big?
I mean,
yeah.
It's going to be determined by however many amps are being required by the motor.
Exactly. If I is equal to 2 amps, is that the same size wire as the one that runs the control circuit? Let's say I do hook this up. I'll just draw some lines, go into this, and we say, oh, this one is 2 milliamps. Because it's a high impedance circuit. It's 2K resistor, 5K, 10K resistor somewhere in there, because all you're trying to do is get high and low signal. But in order to get high and low signal, even an Ethernet cable, it has a voltage and a resistance and a transistor on every single wire, every little one of those wires. Now it's, you're really just reading the high and low, the thresholds of it, but it's a circuit. That's why there's, a wire out and a wire back, because that's how you have to do it. You can't just magically send a signal. The only signal that I know of that you can magically, well, wireless, certainly you could send, right? Bluetooth, smoke signals, you don't need a return. But if it's electrical, it's got to come back. You got to have that wire coming back, or it doesn't work. You can't just send an electrical signal. So stop doing that. But a 2 milliamps is a different wire. How big of a wire do you need for 2 milliamps?
Like 24 gauge or 26 gauge or something?
There you go, 24, 26 gauge, right. How much do you need for 2 amps?
18, maybe. I don't have an Ugly's book handy, but
exactly. But you're on the right track. 2 different numbers, right? 18 is probably good. In fact, if you look at the wiring that I buy, most of the wiring I buy for everything, 18 is small enough to fit in almost all the screw terminals that you're going to come across. So I'll use 18 even in my control circuits, because it's a small enough to fit in there without trying to jam it in. But 18 will also carry, I don't know if you look it up, 3 or 4 amps. It's enough to actually run current through as long as it's stranded. So most of my hookup wiring, I buy 18. You could buy 20, and if you use little motors, but I think if you start getting down to 16, the wires don't fit for universal use. Or you can start, looking at your motor. That's a good indication of what size wire you should attach to your motor wire. At least as big as the motor manufacturer put on there, right? So part of your wiring is, when I look at it, I'm going to look to see if you paid any attention to the wire size that you hooked up. But that's one of the reasons you got to calculate current. Not only blow it up, but also to choose the wires. Okay. So I want you, when I see circuits, this is what I'm going to want to see from you, is something like this that has the schematics that you're using, the schematical part that you're using of the individual components, some labeling, so that, and to me, labeling means it needs to be labeled good enough. if you put this away and you get it out 6 months from now, can you wire it up according to this wiring diagram? Right? So label it and then show how to wire it. And that's your wiring. And don't make it too complicated. If it gets complicated, turn the page and start again. It doesn't take very long to recreate another one of these. You want to count how long it takes to recreate it? I bet I could do another minute. It's pretty quick. So don't make them too complicated, but they sure help you to do it right. So that's what I'm looking for before you turn power on to anything. And after a while, when you do this, you're going to have high confidence that when you turn power on, it works because you went the right way through the transistors and you knew that the current limit was right. And every now and then you'll make a mistake and flip plus and minus, because we all do. I still flip plus and minus sometimes. Well, no. Yeah, probably. So be careful when you're doing that, because that immediately blows things up, obviously. So that's kind of what I'm looking at for your wiring diagrams, is that you've thought it through to the point where you're protected and it's right. Just drawing it from one dot from an input to an output, I'm going to reject that every time. I want to see it come out of a power supply. What power supply are you using? And it's key in mechatronics because we're going to start, we've only got 2 power supplies now, but pretty soon we'll have 4 power supplies that we're using. And each one of them, some are isolated, some will share a ground, but there's specific things that you do. So you've got to start dealing with it in terms of you have multiple supplies and multiple grounding schemes. And that's why you got to, if you come out of one, you got to come back to that one. Okay. Sometimes that means you actually get out a voltmeter. Like on your PS430, that power supply I gave you is a dual power supply. Here's a question for you. Let's say this is the PS430. That power supply that I gave you. It's a common one we use. By the way, it has 2 parts to it. Did you actually look at it? What are the 2 power supplies that are in there? Anybody look at it close enough yet to see what it is? The PS430, it's Applied Motion Products.
Yeah, is one of them like capacitive, and is the other one a different type of power supply?
Yeah, you're on the right track. You're absolutely on the right track there. Yeah, what's that huge capacitor doing on there? We'll get into power supply. I don't think we'll have time for power supplies today, but we'll get you along the way. Why would they put a huge capacitor in a power supply like that?
Store energy.
What's an inductor need, by the way? Inductor needs a whole bunch of current right away.
Sorry, that's right. Mm-hmm.
Yeah, so capacitor charges up slowly, but then you can just grab as much as you want out of it, and it's a great way to charge that inductive load.
Inductive load. Okay.
Right? And if you don't have that, it all has to come from the wall, and that sometimes could be a problem. So any power supply that is good for an inductive load is gonna have good amount of capacitance to it. And that's that big, huge, what's the voltage of that capacitor?
Farad, 10,000 microfarads, 50.
Looks like 50 volts.
There you go.
WV.
Yeah, 50 volts. Okay, so good. And what's the power supply? That part of the power supply, what's it rated at? What's the nominal voltage that you're supposed to get?
Between 220 and 110, depending on where.
Okay, that's input.
That's input, yeah.
That's input. What's the output?
30 volts?
30, yeah. 30 volts, 4 amps.
Now, at what?
30 volts and 4 amps, up to 4 amps.
You need both numbers, don't you? And in fact, this one, we need conditions. And the conditions are a little tricky. It's a linear supply. And this is 100% duty cycle. This is voltage. This is 30 volts. So it's 30 volts at full load. But at no load, over here, at no load, at 0, you can go measure it. It's probably closer to 37 volts, which is a problem. That's a tricky thing about these linear power supplies that do good with inductive loads, is that they're variable and they vary under load. They're not, it's a big transformer under there that in and itself is a I squared R loss. And so the more current you put through it, the more it draws the voltage down. And so it's rated, usually the words rated, nominal, RMS, let's see, what is continuous? You'll see the words continuous. These are all words that generally when they're kind of synonymous, and when so you see something that's a 30 volt power supply, it's probably not the peak. It's probably when, you know, rated means continuous. RMS tends to mean that nominal time, tends to mean at full load or under, you know, when it's being used, versus intermittent, or in this case 0% duty cycle. There's a lot of things that just taking one number as the number is not going to serve your purposes. You've got to get the bigger picture. And so, all right, it's 30 volts when. What about under load? Does it drop or does it raise when it's not under load? So power supplies are actually a little tricky to look at. So it's 30 volts at 4 amps. Okay, that's good. Now, what did you say, Roger, the voltage was of the capacitor? He says 50 volts.
Yeah, 50 volts.
Yeah, 50 volts. So that's an interesting number. Basically what that means is they put in a 50 volt capacitor. There's some other stuff we're going to get into later where that capacitor actually gets charged when you spin the motor backwards. You know what a motor is when you, instead of driving current through it, that you spin the motor shaft and create current? You know what
Generator?
that's called? Yeah, it's a generator, right. Where do you think the energy goes from a generator? The other way.
Grid.
And so at some point when you have a motor that is in both pulling current because there's a load attached to it, but when it gets back driven by the load, like in a deceleration, and the energy's coming back, you got to be able to put that energy somewhere. You don't have that whenever you're dealing with mass. You have stored energy in the mass, mv squared or mv? Energy is mv squared, right? Momentum is mv.
1/2.
Yeah, 1/2 mv squared, right? Is the kinetic energy in the mass. And so whenever you have mass, you have, and you're decelerating it, by the time you get to v equals 0, it has 0 energy, but at v equals 2000, it has lots of energy. Where's it go when it decelerates? Depends. Maybe a little to friction, but that's why it's at 50, not at 30, because it's ready for some amount of energy to come back to the power supply, because that's what it does. It's a generator. All right, the other, so that's one of the inputs. What's the other, or one of the inputs, what's the other output on that thing? By the way, this, does it actually say does it say that word on there anywhere? Unregulated?
I'm looking for that word, but I haven't found it yet.
Okay, all right. Maybe when you get to the data spec on it, see, it's one of the things, just don't use this power supply. You need to go look up, and I believe I put this spec, I believe it's on the 140 website, or you can probably look it up from Applied Motion Products. What's the spec sheet for this power supply? You need to look up the spec sheet for this power supply, because you need to know what it'll do. Okay, so, but this output, the 30 volts is unregulated, meaning it's going to go up and down depending on the load. However, there's also 5 volts on there, isn't there? Can you run an inductive load with that 5 volts? How much current is that? 5 volts at?
Half an amp.
And what does that say? Does that have a word after it?
No.
No.
All right. It should have regulated, but all right, you need to go look it up. Okay.
It does say it on the data sheet.
Okay, good.
It doesn't say it on the not on the actual power supply.
Yeah. So one of the things you got to do when you're starting to deal with these components and learn about them is you can't just take it at face value. There's just too many things going on. You need to read about it, and the words you don't understand, you need to either look them up or come back to me and ask you, what's this mean? Wiring connectors. What I don't want you to ever do is just grab 2 wires and twist them together and put a piece of tape on it. You can do that. You can do that with the loads. You can do that with these kind of resistive loads. You can put a piece of tape on it. And if it comes off, it stops current flowing and it's no big deal. Okay, except for now you probably have one conductor that has power on it and it starts running around, and in at least twice a semester when I was teaching 140, somebody would have, not even 486. Who did it? Somebody blew up like a $3,000 controller last year because a wire came off because they had just kind of twisted it together and they were sloppy. Wire came off and it flopped around until it found the circuit board. And then it shorted out the whole thing. Zzz. Back to repair. So there's special connectors. The ones I love using are by Wago makes them, and they got this little flip latch to them, and you put 2 wires in there and just flip the latch down and it just cinches them together. But they're very handy and the wires don't come out of them. And especially you're going to be doing this when you're hooking up motor wiring. If you have an inductive load and it comes out, that's a really good way to have an energy storage device that can just immediately spike the voltage on a transistor and blow it. Because remember what happens in an inductive load, we're creating electromagnetic fields and you have a voltage that drives the current through it, but every time the current changes, it creates a back voltage in that inductor, that lens voltage. And that lens voltage, when you disconnect it, is a back voltage that blows up what it's ever attached to, depending on which wire comes off. So you got to be really careful with inductive loads because that lens, it's a changing field, and it poof, and it's, you know when you blow things up, it's like already blown up and you can't unblow it up. And the worst part is you only had one. And when you're really doing real machines that you just bought $8,000 worth of components to do a motion control project and you have one of each because they're expensive, all of a sudden that's where this procedure becomes really important. I've had lots of times where it didn't matter that it was a $50 component. It was 6 weeks to get another one. Oh. Okay, I covered off no guessing, and the clues to know you're guessing. Here's the little things that when I call people and ask them technical questions, I call manufacturers all the time. Tell me about, I called, like I was hooking up my own generator. I was swapping out a 5500 for a 4000, and I looked at the connector and I thought, I'll just call Onan, the application engineer at Onan, and say, hey, does this connector on the 4000, it looks like the same pinout, will it control the 4000 the way it did the 5000? Because there's a bunch of switches and timers in there. And he said, yeah, I think that'll work. And you heard the 2 words, right? I think. Or there's the 3-word version of that. I'm pretty sure. You heard that? Or let's see, what's another version of that? I'm guessing obviously is a bad version, but I'm pretty sure, or I think whenever you hear that, that's your signal. You can't do that. You can't guess. You have to, it's like, well, how do we find out for sure if this is the case? Oh, I'm gonna need to go talk to somebody. Okay, can we get them on the line? You know, how do we, do I send, what do you want to do? But so if anytime you hear yourself saying that, I'm pretty sure this is right. You're not done yet. Do not underestimate how these aren't hard, but it's all new and it's all coming together at you. All these different, you know, I'm switching electrical and mechanical, and oh, now we're in the control and the programming, and all comes together here. And so the complexity is kind of high. The individual parts are all easy stuff for you, but bring them together and the complexity kind of goes up. And that takes time for your brain to work through it. Your brains are really good. You're the best of the best. So you can think this stuff, but you've got to give yourself time to think. Design questions that you might have. Components.
So I have a quick question about the wiring diagram that you have up right now. That PWM block that you have coming from your V-bus.
Yeah.
That PWM block is going to be coming from your microcontroller. Your microcontroller is doing that, right?
Yes. Your microcontroller is going to need to do that. And when you really dive into the, I didn't draw the exact circuit of the 298 kind of on purpose, but when you get to the schematic of 298, there's a secret little thing that they put in there that really helps the pulse width modulation part of things. Because you need that transistor right here. The key to this is that transistor has to, you know, I just drew current flowing through it, right? As in DC current, but that's not what you want. You need a way to turn it on and off, and the way to turn it on and off is over in here. There's probably though not a, well, no, I think there probably is a little library thing to run a PWM signal out, right? The question is it fast enough? How do you adjust it? You know, what do you got to do to do that? And then you got to work on the wiring circuit to do that. But the 298N is ready for this. And when you actually get to the schematic of it and study it, it's going to jump off the page at you.